Greetings, programmers. So I'm going to give you a progress report of some stuff that I've been working on. I haven't been working on it for very long, so there's not a lot done yet. So I need to begin with an apology. I have nothing to show you. There's nothing that works. There's nothing you can read. There's nothing to look at. I'm going to tell you what's going on, but that's all there is. I can't tell you when it's going to be done. I can't promise it's ever going to ship. My intention is that it all gets done. It's going to be great, but you know that the intentions of a programmer are meaningless, right? Because we intend for everything to ship. And worst of all, if it turns out that you're interested in the stuff that I'm talking about, there is no way currently that you can participate. And that's inexcusable, completely inexcusable. My excuse is that I was invited to talk about anything that's of interest to me, and this stuff is really interesting to me, so I'm going to share it with you now. And it's all about the web. The web is this amazing platform that grew on top of microprocessors and the internet, which has changed the world. It's everywhere. Everything is going through the web. It's the most amazing thing ever done. But it has a lot of serious problems. And its biggest problem, the thing that concerns me the most, is security. I've been talking for years, traveling all over the world, talking about the security problems on the web and what we need to do to fix them, hoping that somebody would hear me and go off and do it. And I completely failed. That didn't happen. No one has come up to fix the web, so I decided, well, I'll fix it. So that's what I'm going to be talking about. And we can look at the security problems of the web and where we came from. So putting it in a historical context, we can look at passwords. The very first computers were doing top secret work. They were designing weapon systems, they were breaking secret codes, but those machines did not have passwords. The security of those machines was based entirely on physical security. There were people with guns in front of the machine, and you needed to get past them to get to the machine, and there was no other way to access the machine. There were no networks at that time, so that was it. That changes with the invention of the disk drive, because with disk drives, we have online storage. And that means that any program which is currently running in the CPU has access to everything that's on the disk drive, and it may be that program shouldn't have that access. And so passwords start to appear, especially when we get into time sharing. With time sharing, you have a service in which there's a mainframe, and there are lots of subscribers who will rent time on that machine. And generally, they would connect to it using teletypes, dialing in over the telephone network. And the passwords were the mechanism that were used to determine if you were allowed into the machine or not. And they were used for two purposes. One was to make sure that you were not getting into another account's stuff. And the other was to make sure that you were not getting computer time without paying for it. Because in those times, computer time was extremely valuable, not like today. Generally, you would only have a subscription to one time sharing service, so password worked fine. We're all very good at remembering one thing, and that works. But we keep adding more and more things. And so when you got a computer, the first PCs didn't have passwords, but eventually they did. And then we start connecting to the web, and at first the web doesn't have passwords, but then it does, and it turns out you need to give every site a different password. When you were the first site that required a password, it was a completely reasonable thing to say, you got to have a password to get at this site. But how many sites do you have passwords registered with? I can't even count how many I have. And humans cannot remember that many passwords. And so it's a big problem. It leads people to choose bad passwords or to reuse passwords or to be careless about how they manage them because it's too hard. Humans cannot manage more than one of them. So we can look at the history of this in the web. IETF published something called RFC 1738 in 1994, which was the first document to describe URLs. That was a really important document. Everything we've done since then grew up based on that. And it included some syntax for a URL which included a password in the URL, and that password would be sent to the server in the clear. One of the authors of that URL was aware that this was a problem, and so he added this sentence to it: the use of URLs containing passwords that should be secret is clearly unwise, which was an amazing piece of understatement. So he knew this was wrong, but they did not have a better alternative to suggest. Now, some sites took advantage of this and found out very quickly why this was so unwise. So I'm going to be talking about fixing the web, because the web needs fixing. But in order to talk about how to fix it, we have to talk about what's wrong with it. Now, many of you don't know anything except the web. Now, since you've begun living, at least, or working, the web is all you've ever known. And it's going to be shocking and upsetting to you now that I'm going to tell you what's wrong with it. But I need to do that in order to figure out where the web should go. So fundamentally, what's wrong with the web? Two things. The first is that it is insecure, and the second is that it is complex. And I would argue that most of its insecurity is derived from its complexity. The web was not the first hypertext system. The first one was Engelbart's Augment system, which was a brilliant piece of work. Then there was Ted Nelson's Xanadu system, which was also amazing. The web cannot do, will never do, all of the things that those other systems do. But the web was brilliant at being decentralized, and in its first formulation, it was really simple. And the two earlier systems were not. They were very complex. So that wonderful simplicity of the web had a lot to do with why it took off and why it grew and took over. In the years since then, it has been getting more and more complex, because W3C cannot remove any defects from it. All they can do is add more defects to it. That's what the web standards process does. And once a defect gets into the standards and gets buried under other standards, you can't take it out. And so the web keeps getting more and more and more complex. And you can't propose new standards for reducing its complexity, because we cannot remove anything from the web without breaking it. And so it just keeps getting worse and worse and worse. And that complexity is the root of its insecurity. So let's look more specifically at what the web is made out of. First, there's the Hypertext Transport Protocol, HDTV. So in my view, it does three things. First, it's a container format for key value pairs. A browser will send a bunch of key value pairs to the server will send it back some other key value pairs, and that's how that works. I think there are better formats for key value pairs, but HTTP does that. It's also a negotiation framework that the browser and the server need to agree on what formats they want to exchange. This was an important thing in the early days of the web, because not all browsers supported all formats, and so they need to talk to the browser or to the server about, well, this is what I know, I don't know how to do that. And then it's a request-response protocol. So the original view of the web was there's a document on a server, you send a URL to the server, the server sends back the document, disconnects, everything's done. So from the point of view of the client is frozen until the server responds. Well, it turns out that none of our applications look like that today, right? A page contains lots and lots of scripts, it contains lots of images, lots of style sheets, maybe other things. And HTTP wants you to request one thing, and then it'll send it back, and then, only then, can you request the next thing. And so that's really, really slow. So the thing that browsers do in order to mitigate that horrendous behavior is to open up several channels to the same server so they can make requests on all of them, so they can speed it up a little bit, which adds a lot of complexity. Then there's DNS, the domain name system. This was created as a convenience so that people don't have to type in IP addresses, because IP addresses are ugly and not memorable. There are some problems with it. One is that it is not compatible with the trademark system. And so we're constantly having legal problems because we've got these two systems that don't fit. And so we're constantly wrestling there. But worse than that is that it's not trustworthy. We know that there are various DNS confusion attacks which will allow an attacker to force you to go to the wrong address where you could get compromised. And that's a really bad thing. I don't trust DNS. There is SSL, the secure socket layer, which was developed at Netscape in order to provide encryption and authentication, which are critically important things. Unfortunately, the approach that Netscape took to doing this was very, very complicated based on certificate authorities, and it is so complicated that we still haven't gotten it working. After almost 15 years, we still don't have it working right. Almost every month we hear about another major disaster in SSL. If it had been a simpler system, we probably would have finished it by now, but it's still not finished. We still can't trust it. One of the things that's wrong with SSL from my point of view is its reliance on certificate authorities. The certificate authorities will represent that some fact is true. For example, that some party is related to some IP address, and they will cryptographically sign that in order to assert that. The advantage of these certificates is that they can be verified offline. And maybe at the time that SSL was created, that offlineness was desirable, but I don't think it was. I mean, the whole point of being on the internet is that everything is online, we're always connected. It's never important to be checking the security of something if we're not online to use it anyway. I mean, what's the point? But so there's a lot of inefficiency and complexity in the system because of that, but that's not the bad part. The bad part is that I don't trust their certificate authorities. The first of them is VeriSign. I don't trust VeriSign. I don't know who they are. I don't know what they do. All I know for sure is that if they issue a certificate, it means that they accepted money from somebody. I do know from reading Wikipedia that VeriSign has issued certificates which turned out to be bogus, and that they've been hacked, and that they lied about being hacked and still have not come forward about the hackage. That makes me really nervous. But worse than that is that there are hundreds of other certificate authorities. Many of them have been hacked, have been compromised, and we know that they're no good. And your browser trusts all of them equally. And I don't see why we should trust any of them at all. But that's where our security is rooted. Then there's HTML, the hypertext markup language. Is HTML a good thing or a bad thing? It depends on what you're trying to do. If what you're trying to do is to create simple technical documents, which was the thing it was designed to do, it's really terrible. It's hard to use. That's why we invented markdown languages, right? If you just want to, markdown languages are so much more expressive and easier to create. Now, if what you're trying to do is create interactive applications, in particular single-page applications, it's really terrible. It wasn't designed to do that at all. And it does it really badly. It's really complicated. We have all, as an industry, spent a couple of decades trying to figure out how to use HTML effectively. And it's amazing how ingenious we've been at figuring out how to use this thing. But it's still really bad fundamentally. The thing that I hate most about HTML is that it inspires a style of application development based on templating. I hate templating for three really good reasons. The first one is it is where XSS attacks come from. It's possible to create a templating system which is not subject to XSS code injection, but they all allow it, and apparently they all practice it. We see XSS problems happening every day, and we know how terrible they are and why they need to be prevented, but a templating framework just really wants to take some raw text and put it out and cause bad things to happen. The other, number two, is that everything becomes HTML. It's all about, the whole pipeline is about producing HTML. So you start getting layer leakage, where you've got this multi-tiered system, and every tier is concerned about, we're going to make HTML. Everything's making HTML. It's HTML all the way down. And if you've ever worked in any other technology, any non-HTML technology, you know there are much better ways to make applications. But we've got this huge fixation on HTML because that's what everything's made out of. The third thing is that it's a trap. If everything in the pipeline is all focused on making HTML, we're never going to get free of it, right? If someone were to come to you and say, we've got a much better way of making applications, say, but is it HTML? You can't even imagine it. You just can't work with it. Then there's the document object model, or the DOM, which is, I'm pretty confident in saying this, I think it's the worst API ever invented. It's just awful. It's just awful. And on top of all of the terrible performance problems and the reliability problems and the portability problems, all the stuff, it is horrendously insecure. If an attacker can get access to any node, it gets access to every node and the network, and it's all lost. It's a terrible model. Then there's CSS, the crappy style sheets. I don't have to tell, I could rant, but I'm not going to rant. You know what's wrong with CSS. I mean, it's the lack of modularity and the weirdness and stuff. It's possible to make CSS do stuff, and once people figure out how to do that, it's like, wow, I'm so smart, I made CSS work. And it's really easy to forget what you had to do in order to get that to happen. And you should never have had to do that. There should be much more straightforward ways of doing things. Again, CSS was not designed to do applications. It was designed to do technical documents. And it's remarkable how ingenious we've all been at making this stuff work, but that's not what it was for. And there's JavaScript. JavaScript is a hot mess. And it's getting messier. So last week, in Italy, the ECMA General Assembly finally approved what's going to become known as ES15. Next year, there'll probably be an ES16. There are some good parts in ES15, and there might even be some good parts in ES16 and 17 and 18. But there's going to be some bad parts too, and it just keeps getting bigger and bigger. The good news is that there's a good language inside of ECMAScript, inside of JavaScript. And we can write in that language, and it's possible to write good programs in that language. I'm hoping that someday we're going to get rid of JavaScript, because I'm really tired of JavaScript. But we're not there yet. But in the meantime, it's better than pretty much everything else. So, okay, so we'll use that. I want to get rid of everything else, but I'll keep JavaScript, but try to get rid of everything else. Now, there have been many companies who have tried to replace or capture the web. Microsoft, Apple, Adobe, Oracle, and many others, big and small, have all tried to make their own application platform on the theory that it's easy to do something that's smarter than the web, so we'll just do that. And they're right. There are lots of ways to do things that are smarter than the web. So their technology is usually better, but in most cases, the solution is not open, because what they're trying to do is to capture the thing. They're trying to turn what's the world's biggest open system into a closed proprietary system. And fortunately, they've all failed. That none of them have managed to do that. And I think the reason they failed wasn't because their technology wasn't good, and it wasn't because their hearts were not pure. It was because they didn't have a transition plan. They thought about transition in terms of, how do we get you, the developers, writing into their system? They figured if they can capture you, then they capture the world. But that turns out to be the wrong model, right? I think they've demonstrated that. So my plan is I want to upgrade the web. I don't want to replace it. I don't want to capture it. I want to keep the web in place. I want to keep the web open. I want it to continue to do the things that it does well, but I want to fix the things that it does really badly. And I want to make it work for everybody and for you. So my model for how to do this is based on high-definition television. The first television system in the United States was an analog system called NTSC, which stood for Never Twice the Same Color. And it became a mass medium. It was incredibly popular. Even back when there were only 3 stations, we watched it all the time. It was great, even though we couldn't see it very well. And eventually, we decided we need to go to a new digital system. The Japanese have been working on high-definition television, and I'm not going to tell you the story about why we actually got into high definition because it's kind of sleazy, but we decided to do it anyway. And there was a lot of concern about how the transition was going to happen. Because at some day and date, the FCC was going to have to say, broadcasters, stop broadcasting on the analog channels, and everything from this point is going to be digital. So on January 1st of some year, we do the switchover. And a couple of weeks later, there's going to be the Super Bowl. And if a significant portion of the country is blacked out because their analog TV sets cannot watch the Super Bowl in digital broadcasting, there's going to be an armed rebellion. And there's an argument that maybe that should have happened some time ago, but it hasn't, because we've been watching television. But when the television stops, it all falls apart. So they were really worried about it, that how do we manage this transition so that the country doesn't turn on us? And there was a lot of nervousness at the FCC, in Congress. The Supreme Court was involved in it at various times. How do we make sure that the transition goes well? The key to the transition was something called the set-top box. The set-top box was something that you'd put on top of your analog TV. Analog TVs, it turned out, were very deep boxes, and so there was a big place on top where you could put a box. It's because the picture tube stuck out the back. And that box would receive digital signals and make them visible on your analog TV. Now, some of the set-top boxes would be provided to you by your cable company or your satellite company, but in the case where you didn't have one of those, the government would supply you with a free set-top box so that you could watch the new digital shows on your analog TV. And they designed it such that you didn't know which kind of TV you were watching. You might have noticed that turning channels suddenly became really slow when you're in digital TV, or you might notice the digital TV pictures looked better. But otherwise, there was nothing. There was no mode switch. There was no different UI. It just was the same thing. And it worked. That transition worked. So that's my metaphor for how this web transition should work. My set-top box in this analogy is the Helper app. Anybody remember Helper apps? Some of the old timers. The first web browsers didn't know how to do very much. So if they were given a data type or a URL of something that they didn't recognize, they could pass that to another application. For example, if you gave them an address of a ping file and they didn't know what ping files were yet, they would open up your Paint program and it would show the thing. Or they could do similar things for playing sounds or for sending email. And most of the browsers still have an affordance for helper apps built into them. They just don't use it very well, or don't use it at all because we don't pay any attention to that anymore. But it's still there, and we can use it. So this is my transition plan. Step one, I need to convince one progressive browser maker to integrate my helper app, my set-top box. That I want to build this app or this helper and distribute it And I'm very confident that the mainstream of humanity will not install it, because they never do. They don't want to install anything. You might be curious and you might want to see how it works, and so you might try it. And if enough of you look at it and goes, yeah, there's some promise in here, then one of the browser makers may integrate it, either because they see the value in it or they want to get some market share, and there's a chance that maybe this is a way that they could grow. Then I need to convince one secure site, probably a financial institution, maybe a government or a medical thing, something that has a real deep concern for security, and convince them to require their customers, at least for that application, to use that new browser so they can get into this new mode. If that is successful, then I believe that risk mitigation will compel other secure sites to do the same thing, that they will begin to transition their most critical applications to this new mode and require people use that new browser in order to access it. And then competitive pressure will move the other browser makers to do the same thing. Integration of the helper app should be really easy, because all the helper app needs is a rectangle on the screen and events coming from the UI and the ability to send JSON messages back and forth, sort of a post message thing. That's all. The helper app will do everything else that it needs. Then I expect the world will follow for improved security and faster application development, because I think once we get away from HTML, application development becomes a lot easier. And nothing breaks. So I'm proposing no change at all, no changes at all to the current HTML stack. All of that stuff stays exactly in place. I'm not asking for any new complexity, no new modes, none of that stuff. Just this other thing which is accessed differently. This new thing will be built with strong cryptography. Now, strong cryptography is not a guarantee of security. It turns out, well, I don't need to tell you the story. Strong systems get broken all the time. But I want to use strong cryptography. In fact, I'm using cryptography which is much stronger than I need. Just because of recent events, I'm getting paranoid, and so I'm putting more strength into it. So elliptic curve 521 for key exchange and authentication, AES 256 for link encryption, and SHA-3 256 for hashing. There's a guy named Zuko who has a theory about naming systems. He says that in a naming system, there are 3 desirable properties: that the name be human meaningful, that it be securely unique and globally decentralized, and you can get at most 2 of them. The one that the web got was human meaningful. And I think it got that just kind of borderline. So URL is a human meaningful name that gets you to a thing. I'm more concerned about security, so I'm going with the other 2. I want names which are securely unique with a system which is global and decentralized, with no center authority for approving or issuing names. So I'm going to be using elliptic curve 521 public keys as globally unique identifiers. So the way you will identify yourself in this new system is with this 105-digit number in base 32, which is something that a human can't type something that's that long. So it's going to be really ugly, but it's you. It's guaranteed to be unique. And the way you prove that it's yours is that you have the corresponding private key. So you can decrypt messages which are sent to you that are encrypted in your public key. And that will be the way you identify yourself. There will be no passwords in this system. Well, I take that back. There'll be one password in the system, but that password will never be sent over the wire. So we're going to get rid of HTTP and SSL and replace it with secure JSON over TCP. TCP, I think, is one of the smartest things that has ever been developed, and it's just great. So I just want to do that and put JSON and blobs on the wire, and that'll go really fast. It will also get rid of the request-response trap in HTTP, so that you'll be able to send as many messages as you want to a server, The server can send you back things anytime it wants. It will now be asynchronous. It's not going to be in lockstep. So if the server has something to tell you, it can just tell you. It doesn't have to wait for you to ask. So it's going to be much more flexible. We can do a much broader class of applications than we can easily do over HTTP. This is the URL that we'll use to get into this new system. So you could put one of these URLs on your page, and the next thing that'll happen is if someone clicks on this, the helper app will start up, and the next thing they see will be the response from the server from this thing. The scheme in this one is web. I think that's what the web should have used web, right? It should have been web : not HTTP : So since they didn't use it, I'm going to use it. I don't know that I'm going to get away with that. I'll probably have to give it a different name. But for now, I'm calling it the web. And then you'll have your 105-character public key, then an @ sign, and then an IP address, which could be one of the new ones or one of the old ones. And then optionally a slash and a capability, which will be some thing which uniquely identifies you, so that, for example, your bank could give you a card that has one of these encrypted on the back, in a QR code, and you just scan that into your device, and now, boom, you're fully connected. They know who you are. You've exchanged private key or public keys. Everything's great. I don't trust DNS to get the IP address, so we're making the IP address explicit. I don't trust VeriSign for verifying the public key, so we make the public key explicit. Another way you might get these is from Google, because while I don't trust VeriSign, I do trust Google. So if I ask Google, what's this guy's credentials or address, I trust Google to tell me that. They're really good at compiling that stuff, and they seem to be comparatively honest. So we'll go with that. And if it turns out they're not, then we'll go with Bing or Yahoo or, but I think Google's going to be good on this. So this URL is going to be impossibly difficult for humans to manage. So we'll provide some additional support to make it easier. We'll provide a trust management system which will keep all of your credentials and relationships in the cloud in a way which will be safe, so that once you've established an identity or a relationship on any of your devices, it will be available to you on all of your devices, but not to anybody else. We'll also provide a pet name system so that you don't have to remember the 105-digit keys, that you can give it a nice little friendly name, which is just your name for that thing, and no one else sees it. It makes the system a lot easier. Our model for computation in this will be the vat. The vat is a container made out of iron, which we can control, that nothing gets into the vat, nothing gets out of the vat except through the proper channels. I wish VAT stood for something, like it should be a virtual something, but it doesn't. It's just a VAT. It's a much stronger container than a sandbox. The problem with sandboxes is that they leak, and if you have a cat like I do, you don't like that. So all computation in this model will be in VATs, and every party that might be involved in something gets its own VAT. So this allows us to finally have secure mashups, where we can have several parties all working together cooperatively in order to make a transaction or create value for the user, and none of them can corrupt or confuse the other because they are all running in their independent VATs, and then they cooperate by exchanging JSON messages between each other. So this allows us to have a model of computation called cooperation under mutual suspicion, which will be great. That we, because I have a hard time trusting things. And with this model, I don't have to. I can just put your code in a vat and give it an API and know that it can only do the things that my API allows it to do, and I don't have to trust it. It can't do anything worse than what I allow it to do. So this is the block diagram for this system. And it's a really simple block diagram. There are only 2 blocks in it. So this is what's in a helper app. There will be a JavaScript message server, probably Node.js. It might be another one. I'm hoping someone will write a newer one. I've got some problems with Node. One is that it is way over specialized for HTTP, and I'm not doing any of that, so I don't need to pay for that. The other is that I have much higher security requirements than Node has. And so I'm going to have to go through everything in Node and do an audit and lock things down and modify things. And it would be easier if I could work with somebody's system that was built from the ground up to have the security properties that I need. But if that turns out not to appear, Node will work just fine. I'll probably have to change some things, like I don't know yet if I can use NPM, because NPM wants to be able to load code from any place and that can do anything. And you can't really do that in a secure environment. We need to be much more cautious. On the other side is Qt. Qt is an application framework that was developed in Norway. It belonged to Nokia for a while, but now it's open. It's a really nice way to build applications. I'm not taking the entire Qt system, just the stuff that does displays and interactivity. So you'll be able to, on the Qt side, you will have your visual presentation and your interaction, and then you'll send JSON messages over to the other side in order to mess with the model and to communicate things to the server. And so you got messages going back and forth. I see a lot of confusion in the HTML world where everything is happening in the same, even in the same object. The same object is manipulating imagery and keeping state. That's bad architecture. So in this case, I get to actually enforce good architecture. I have visual VATs on the Qt side, but the Qt side has no access to the file system, has no access to the network. Then on the other side, we've got access to the file system and the network, but we don't have access to this display. So you take your application and you cleanly divide it between these 2 aspects. So I'm not proposing getting rid of the web. The web is really good at promiscuity, that you can go out and connect to a whole bunch of stuff. And as long as you're running no script, that's a safe thing to do. But it turns out that model is not good for managed relationships. So if you're talking to your bank or to your doctor or other things, you really don't want that promiscuity model. You want something more solid. And so I'm proposing a new web for managing commitments, where I've got these really important relationships with really important parties, people I have an ongoing thing with, and I want to make sure that every time I communicate with that, I am communicating with the same thing, and that they know they're communicating with me, and we can guarantee that. And that's something that the web in its current form can't do. So we need the promiscuity part because that's how we make the connections. But once the connection's made, I think we want to go to this more committed relationship. So architecturally, there's nothing new here. Everything I'm talking about, there are no new discoveries. It's based on research that's been going on for decades. I'm just applying it to the web in a way that I think could transition into a successful deployment, which is something that no one else has managed to do yet. So in the meantime, keep doing what you're doing. I'm not proposing that you change anything. I'm not saying, stop, this is coming, change everything, throw it all out, start over, this is the way you want to go. I'm not telling you that. I'm not telling you that. There used to be a thing called FUD, fear, uncertainty, and doubt. So Control Data introduced a new mainframe, the fastest computer in the world. IBM said, oh, we got to compete with that. They had nothing. So they announced, we've got a new machine coming out that's faster than the Control Data machine. Just wait for it. They didn't have it. Control Data eventually took them to court and won and got millions, and good for them. But IBM kept doing that. It's also been called vaporware, where you're making stuff but you don't have it, but you announce that you have it or are about to have it in order to keep people from going to your competitors. Microsoft used to do this stuff. It's really, really bad practice. That's not what I'm doing. I'm not saying that this will ever happen, and if it happens, it's just, wait, this is so early. I shouldn't even be talking about this, but this is really interesting to me, and I just want to share it with you. So this might happen someday. So, so what I'm offering you, I hope, is some hope that maybe eventually we'll figure out a way to make secure applications that we can develop at a reasonable cost with reasonable risk on the same web that we're working with today. I can't figure out any other way to do it, because any other approach is going to want to add more complexity to the current web, and ultimately, we can't get there by adding more complexity. We have to get to another kind of thing, but do that without sabotaging the first thing, because there's a huge amount of value in the first thing. That's my message for you today. So until next time, keep calm and JSON. Thank you, and good night.